So I think we'll go ahead and get started here this morning. Updates as far as due dates, things like that to be kind of considering. I believe the lab 5 is due last night, so that one's passed. But homework wise, I believe the chapter 15 is due tonight. We're going to see for the next couple nights. Chapter 16 due tomorrow. However, our exam is tomorrow, so definitely be working on that tonight. That way, if you have questions on any of that for tomorrow. And kind of along a similar line, chapter 17 are broken into 2 parts. Part 1 is going to be due Thursday. We are going to cover a good bit of that, I think. Really, we kind of got an introduction to like finding pH of one thing yesterday, and so we'll kind of continue with some start of today. By the end of the day, hopefully we're looking at finding pH of multiple things, which is really the start of chapter 17. And so that kind of focus on those types of calculations. Those types of problems, if we get to them today, probably will be on tomorrow's exam. So it's worth looking at them, but I did kind of give some extra time to kind of go through and look at it. And that assignment is not very long. It's only like 4 or 5 questions, if I remember right. Exam 3, right, it's tomorrow. All of chapters 15 and 16 for sure. We'll see kind of where we are as far as how much 17 ends up there. My guess is just kind of a very brief bit on kind of buffers and like mixed solutions finding pH. And then for the lab side, the labs we just did yesterday, lab 6 and 7, have to do is Thursday, just so it's not so overwhelming tomorrow to have an exam and a whole bunch of stuff due. We will do lab 8 tomorrow. It will probably have a pre-lab quiz, mainly just because I think the topic of that one will actually be like kind of what we're doing tomorrow by the end, or not tomorrow, Thursday by the end of that lecture. But that will be probably our last pre-lab quiz. I know we've only had them for a few of them this semester. The lab we do next week will not have a pre-lab quiz attached to it with electrochem because you'll probably be doing that experiment before we fully see all of that in lecture, unfortunately, just so we can kind of get everything in and kind of scheduled. That's kind of the quick refresh and kind of what's coming up due here. So where we left off yesterday, we've kind of gotten to into chapter 16. We've been talking about kind of reviewing some stuff with acids and bases, kind of reviewed some things with naming, and it just kind of introduced these ideas of like Ka, Kb, Kw, and pH. So what I want to do kind of as a starting point today is look at kind of just what are we using some of that stuff for? What are some of the kind of calculations you want to be used to doing? And really the starting points for most of these, and probably the majority of the questions we're going to see out of from a calculation sense in chapter 16, 17 are all about finding pH. Like how do we calculate pH of a particular solution? So we'll take a look at kind of some examples here. This is similar to kind of what we were ending yesterday with, although looking for kind of a different piece. So here we're asked, what is the pH of a 0.400 molar solution of HF? And they give us that the Ka of HF is 6.8 times 10 to the minus 4. So some things that I want people to kind of get in the habit of looking at, whenever we're asked to find the pH of something, first off, how many things are in the solution? Because if it's just 1, that tends to be a little bit easier. As soon as it's 2, then there's usually other complications we'll have to consider, and that'll be kind of what we get into at the end of the day of chapter 17. But when it's just one thing that's in solution, the other thing to focus on is what is that thing? Is it an acid? Is it a base? Is it strong? Is it weak? And how do we know? So in this case, we have HF as our compound. What would that be in terms of acid base? That's the easy part. It's an acid, right? There's a hydrogen listed first in the formula, so probably an acid. What's the other clue this is an acid? You have a Ka, which means not only is it an acid, it's what kind of acid? Yeah, it's weak, right? If you have a Ka value for it, it's going to be weak. If you see a question asking, we'll see this in a second, like what's the pH of something and there's no Ka or no Kb, then what you're looking at is probably strong. So you should figure out is that a strong acid or a base kind of for the next steps. Now, for this one, since we have the Ka value, that means it's a weak acid. So it does not totally dissociate. And if our goal is to find pH, what is it that we really need to know? What we need to find is not the concentration of HF, but the concentration of H plus or H3O plus, depending on which way we write a lot of these equations. And so our goal to find pH is to find that H3O plus concentration. So our starting point is, since we have this Ka value, we really need to write a reaction for what's happening. And then it's going to be basically an ice table calculation. And so anytime you have one thing in solution like this, if it's a weak acid or a weak base, like you're pretty much going to have to do an ice table, which means write the reaction that's going to occur. Show kind of both variations of this, because we'll see some examples before this. But for Ka, what's the reaction that's involved for Ka? It's going to be HF. I usually include the water, so it'll be like HF plus water. So what would my products be? What's that going to produce? Yeah, good. So we have HF plus water. It's going to, anytime you have a Ka, one of those products effectively has to be H3O plus. And our other product in this case should be the conjugate base of our acid once it's lost that proton, right? HF, the starting acid, and leave behind the F minus as its conjugate base. So if I go to put things in here for our ice table, we have an initial concentration of 0.400 molar for the HF. For our water, for all of these, and this is why sometimes you'll actually even just say like HF going to H plus plus F minus for a lot of references. They'll just leave the water out kind of entirely because it does get canceled out even if we show it this way. And we don't have any of our products to start out with. And so now we're kind of back to almost chapter 15 things. We have an ice table. We need to fill out the rest of the ice table. The nice thing about all of this acid-base stuff, all of the coefficients are 1. So that's at least kind of nice to work with. So in that case, our reaction has to go forward, which means minus X plus X plus X, filling things out. So that 0.400 minus X, X, and X at equilibrium. Everyone okay with that part? Yeah, as soon as you see a 0 initially on either side, that like it's always got to go towards when we have 0. All right, from here, how do I go about trying to solve for that X? I don't have any equilibrium amounts right now. And really my goal is I kind of want X because that's the H3O plus concentration, so I can use that to find pH, right? That's kind of the end goal. Good. So our Ka value needs to equal X squared over 0.400 minus X. And where that's coming from is just Ka is our equilibrium constant. It's products over reactants, right? So X times X over the 0.400 minus X. But our Ka value that they gave us is 6.8 times 10 to the minus 4. So in terms of making our life easier here, what are we able to do? Yeah, we can use that X is small approximation. How does that change the setup for us to make this easier? Yeah, we get to ignore basically this minus X. Right? We have a 3 power of 10 difference between that initial concentration here and our actual equilibrium constant. So we should be able to use X is small. We're going to ignore the minus X part. And that just makes the algebra here a whole lot easier. You don't have to set up any quadratics or anything like that. We can simply multiply that 0.4 across and then take the square root, right? So X would equal square root of 6.8 times 10 to the minus 4th times that 0.400. So we can get a number for that quick. So if we do 6.8 times 10 to the minus 4th times 0.4. Take the square root of that. Get about like 0.0165. And remember, in this case, our X is equal to the H3O plus concentration. And so now if we know the H3O plus concentration, our end goal, finding pH, how do we get pH again? Yeah, just the negative log of H3O plus. So negative log of 0.0165. we can get our pH. So it's about 1.78. And if we stop to think for a second, in terms of our pH scale, we started with an acid, right, HF. And in terms of concentrations, we started with 0.40 molar. That's a reasonably high concentration, honestly. If you start getting around 1 molar, that's a pretty high concentration for an acid. So we should expect a fairly low pH, right? Acidic solutions, your pH is under 7. Kind of the stronger the acids are and the higher the concentrations get, the lower that pH is going to get, to the point where pH actually can't even get negative. If you have a concentration like a strong acid that's over 1 molar, like the pH actually will be negative. Like that can happen. Most people kind of think that, oh, it's like you can't have negative pH. Like you can, it's just a very concentrated acidic solution. Likewise, I think people tend to think that for some reason the pH scale caps at 14 going the other way. If you have a strong base with a concentration over 1 molar, your pH can go higher than 14 as well. They're not very common to have those situations, but it is possible. But high concentration of either strong or at least kind of like stronger side of weak acids, which HF is kind of in that area, like 10 to the minus 4th for a Ka. As far as weak acids go, is actually kind of a big Ka. A lot of Kas can go all the way down like 10 to the minus 9th, 10th, 12th, and even lower. And so, 10 to the minus 4th. As far as weak acids go, it's actually a little bit on the stronger side. So getting a pH that's down at 1.78 seems kind of reasonable. And if we check this to make sure we didn't, as I say these things, to make sure we didn't butcher anything up, we have 1.79. So maybe some slight different rounding. Whenever, oh, they actually did the quadratic, that's fine. 3 powers of 10, I don't think the quadratic's really necessary here. So, right. Questions then on any of the setup that we kind of went through for this? Probably the biggest things I would get used to looking at is as we start seeing these problems where it's like find the pH of whatever, figure out what is that thing that's in the solution. Is it an acid? Is it a base? If it's just one thing and it's weak, you're going to have to do an ice table. As we get to the end of the day and we have multiple things, we'll see that we may have a different type of table that will start with like a BCA that'll tie into kind of neutralization reactions in particular. We'll kind of look at those examples as we get there. But just one thing, if it's weak, have to do an ice table. We'll take a look at kind of the base side of things here too. So if we take a look, for instance, at the next couple active examples, we can see some examples of dealing with bases. So if I want to find the pH of a base, this will let us also kind of relate some different things here together from yesterday that we maybe didn't do as much with yet. But in this case, we want to know the pH of a 2.5 times 10 to the minus 4 molar solution of cesium hydroxide. So let's start with what exactly is cesium hydroxide as far as acid, base, strong, or weak? Yeah, it is a strong base. How do we know it's a strong base? Yeah, first off, there's no hydrogen like listed by itself like out in front, so it's probably not an acid. Additionally, it's got a hydroxide there, so definitely a base. If there's no Kb given right there, it's probably a strong base. And your other kind of trend there, all the group 1 metals are strong bases when paired with the hydroxide. They're all soluble basically. That's what makes it a strong base. So we definitely have a strong base here. So if I want to find pH, there's actually kind of 2 options in this case. They're both going to kind of still tie in a little bit to things we talked about yesterday. Although one is an equation we didn't really mention, but I think is actually going to be kind of the easier way to usually approach these. So I'll write what it gave us here. So it's 2.5 times 10 to the minus 4th cesium hydroxide, looking for the pH. So before I actually kind of set up this specific example to kind of solve, I do want to mention a couple of things here. In terms of how hydroxide concentrations and H3O plus concentrations are related, we had one equation yesterday that was Kw equals the H3O plus times the hydroxide concentration. That applies to any solution, not just plain water. Even if other things are there, that applies. Meaning as H3O plus goes up, OH minus goes down, and vice versa. That'll always be true for any solution. There's one other kind of variant of this equation that we can kind of put together. We said that pH is the negative log of the H3O plus concentration. But really, P kind of with anything after it is just the negative log of what's after that listed. So for instance, POH would be the negative log of the hydroxide concentration. Well, it turns out if I take this KW equation and just take the negative log of basically all of it, one of the ways I could simplify this is that it turns out that pH plus POH is actually going to be equal to 14, always, because of how the OH and H3O plus concentrations are actually related through that KW, right? Because KW is a constant, it's like 1.0 times 10 to the minus 14th. So if I take the negative log of that whole kind of top equation and rearrange things a bit, I can get to pH plus POH should be 14. So for me, whenever we have to find the pH of a base solution, usually if you have a base, it's pretty easy to find, or it's easier to find the hydroxide concentration. Well, I think the easiest thing to do to find pH then is just find POH by taking the negative log of the hydroxide concentration and then just subtract that from 14 to find pH. I think that's usually an easier process, because the alternative is if you find the hydroxide concentration, you'd have to use this equation to find H3O plus and then do the negative log of that, which I think is just two harder calculations that you're probably gonna need a calculator for both of them. Whereas if you find the POH first, I think this bottom equation is one most of us can do without a calculator a lot of the time if you're comfortable with it. That's just, I think, an easier kind of step that's kind of doing it, but you can do it either way. So for our example that we started with in here, where we had this 2.5 times 10 to the minus 4th molar cesium hydroxide, if that's our starting concentration, what does that tell us about the hydroxide concentration that's there? If it's a strong base, like we said before, the hydroxide concentration should just be the same, right? That same concentration. So because cesium hydroxide is a strong base, we can basically say that the hydroxide concentration itself is equal to that same 2.5 times 10 to the minus 4th molar. Which means now in terms of finding pH, we can kind of go the different routes that I mentioned. We can use that to find H3O plus with KW and then do the negative log of that. Or personally, I think it's easier to just go straight to a POH. Take the negative log of 2.5 times 10 to the minus 4th. Negative log 2.5 times 10 to the minus 4th. Looks like it's about 3.60. And then if I want my pH, my pH would be 14 minus the POH. So 14 minus 3.60, which would be about 10.40. And hopefully that should kind of make sense. Again, if we have a base solution, we expect the final pH to be bigger than 7, and that is what we're seeing. And the only reason that pH probably isn't even higher is that the concentration is 10 to the minus 4th, which is relatively small. Otherwise, we'd probably see a higher pH at a higher base concentration. Right. Questions on what we did with that? And like I said, you do have the option if you wanted, once you had this hydroxide concentration, you kind of recognize that the cesium hydroxide is a strong base and that that's our OH concentration. You could use KW to just find H3O plus through this equation up here, and then take the negative log of H3O plus and get the exact same answer. It should come out the same either way. So whichever way is more comfortable or easier for you. Personally, I just like going the POH route. It's kind of what I've always done. I think it's what most people, once they've kind of seen these examples, tend to gravitate towards. But the biggest thing is just realizing that when you have a base, the concentration of what you're solving for initially usually is going to be hydroxide, not H3O plus. So you kind of have an extra kind of step there towards the end. All right. If we look at, I'm going to do one more example because this is something that comes up for bases more specifically rather than the acids. What if we have a very similar question here? Here we want to know what, and this time it's actually asking about the POH, not the pH, but it wants to know the POH of a 0.02 molar solution of strontium hydroxide. So first off, again, one thing in solution, there's only that one compound. So what is it in terms of acid, base, strong, or weak? Yeah, it's a base and it's strong. And again, there's no KB value, so that's kind of the clue. Usually it's probably going to be strong. Now, what do we have to be careful about in this case for our hydroxide concentration compared to the last example? And this is something that's kind of unique to bases rather than acids. How many hydroxides does this compound have? Yeah, 2. So if it's a strong base, the concentration of OH minus is not 0.02, but 0.04. We have to double it. Right? So that's probably the biggest catch here to just be careful with. We can have bases that have multiple hydroxides. And we do have acids that can have more than one proton, but we'll talk about that shortly here. It's not something where it's going to work the same. Like acids with multiple protons usually are not just going to give off all of them at once, like kind of a base will. So in this case, we had 0.0200 molar strontium hydroxide, which we said is a strong base. So our concentration of the hydroxide is actually 0.0400 molar because there's those 2 hydroxides. That's probably the catch to this particular problem. And now from here, if it just wants POH, well, that's just the negative log of that OH concentration. So negative log of 0.0400. And just quick sig fig things, like the previous example, like the concentration had 2 significant digits. That's why we had 2 decimal places, remember, in the pH. pH or sig figs are all after the decimal place. So here, if we really technically have 3 significant digits in our concentration, that means we're actually going to get 3 decimal places technically for this POH. Whether active actually is being that picky on them, I don't know. I'll find out in a second. What's that? It wasn't. Yeah. So POH, if we get this then, calculate this real fast. So negative log 0.04. It's like about 1.398. I guess if we're being really technical with it. No, that's actually what it says, 1.398. It probably accepts things with 2 sig figs, I'm guessing, though. But if we're being really, really picky on sig figs, like the number of decimal places on those pHs or POHs, those are your actual sig figs for the machines. Okay. Questions on first couple strong bases here? I'm going to do one more. It's a weak base, so we can kind of just see what's going on with it. But really nothing too different for it. So if we look at, this is the 4th one that's up for today. So here we're asked, what is the hydroxide concentration? So not even the pH, just the hydroxide concentration. I'll probably have us just calculate the pH just for habit too. But what is the OH concentration of a 1.40 molar solution of pyridine? And they give us that, the chemical formula of pyridine there and the Kb value. So again, one just thing in our solution, we kind of need to know what it is. Well, as soon as they show a Kb value like this, what does that tell us? Yeah, it's a weak base. So we're looking at a weak base. And really, you don't even have to give us the chemical formula. If they just what's the pH of this concentration of a pyridine solution, just give us a Kb, then we can just assume the pyridine's a weak base. We don't really even need to know the formula for that specific. All right, so I'm just gonna write this down. We have 1.40 molar pyridine. Tell us Kb is 1.70 times 10 to the minus 9th. So we have this one thing that's a weak base, and as soon as what we're looking at is weak and not a strong base like our previous examples or a strong acid, if we're looking at something that's weak, that does mean ice table. That's going to be our starting point. Now, reaction, whenever we're going to make an ice table, or really any table for kind of these couple of chapters that we're getting into, we need to know what is the reaction that's happening. So what would our reaction look like in this case, since we're dealing with a Kb and not a Ka? What changes? And for pyridine, we don't even have to be very specific. I'm just going to write B for a base, right? And for all of our Kas or Kbs, it's basically just what happens if we put these things in water. So our reaction is our base. I'm putting it in water. But since it's a base, what are my products going to look like? If it's a base, it's really a base because one of the products has to be hydroxide. And the other product then is just the conjugate acid of whatever our base was. So we're adding a proton to that base, giving it a plus charge like that, right? So that would be kind of our generic reaction for any weak base equilibrium. We saw kind of the generic reaction for any weak acid equilibrium up above here. Basically replace the F with an A, and you can do that for any acid, just that same kind of notation. All right, so putting them together our ice table then, they gave us an initial concentration. They said it was 1.40 molar. Water being a pure liquid, get to ignore. Right, we'll put physical states on all of these. Everything's aqueous except the water. And we don't have any hydroxide or the conjugate acid there to start with. So really filling out this ice table, these start to get kind of repetitive for a lot of these chapter 16 examples because there usually isn't anything on the product side yet. So minus X in the reactants, plus X on the product side. So we'll get 1.40 minus X, X, and X. And now we have a KB value. Right, the problem told us that KB was equal to 1.70 times 10 to the minus 9th. And how is that helping us here? What is that going to be equal to? Yeah, so it'll be equal to x squared over 1.40 minus x, right? Products over reactants. But that minus x in that denominator there, because that KB is so tiny, we can again just kind of use x is small. So we'll use our x is small approximation to get to ignore that minus x. Because this reaction with the equilibrium constant that tiny definitely is not going very far forward. And from here, now the actual math, I want to solve for x. X would be 1.70 times 10 to the minus 9th times 1.40. And then we're taking all of that to the 1/2, which is the same as taking the square root of all of it. So I get a number for that real quick. We'll have 1.70 times 10 to the minus 9th times 1.4. We're taking the square root of that. Take about 4.88 maybe times 10 to the minus 5th. So that's our x value. But remember, this is, if we're asked, what we were asked for was the hydroxide concentration. X is the hydroxide concentration, so you can have units of molarity would be the units of that for that concentration. And that's where I think active ends. It's not asking for more beyond that. But if I want to define pH, because that it probably is the more common thing to get asked for, what would I do as a last kind of couple steps to find the pH then from this point? I could take negative log to find POH and then just subtract that from 14 is probably kind of the usual ending there. And so do kind of as you get to the end, like pH is probably thing it's going to be asked for 90+% of the time in most problems. So when you have a base that you started with, just be aware that what you end in, like the X you normally solve for is a hydroxide concentration. And so you do have to kind of take that one extra step to get to pH. Because a lot of people get to this point, just do negative log and stop. But negative log of that is POH, not pH, right? And so one thing that can help with that is like if you started out at the beginning recognizing that that's a weak base, you better end at the pH that's bigger than 7, right? If you just do the negative log of what's here, you're probably going to get, you know, a POH that's like 6 something or something like that, which that's not a basic pH, which is why you'd have to then subtract that, and then you would get a pH over 7. Questions though at all going through that example? All right, there's one other kind of, I think, coming from a calculational sense, solution that we can kind of encounter, and that is a polyprotic acid. So first off, polyprotic acids. Do we know what that would be or what that is? What's it sound like? Poly just usually means many. Protic probably means proton, so it's something that's got multiple protons it can lose, or multiple acidic protons. So we're basically talking about multiple H plus that can be lost. And you usually can know that there's more than one proton that can be lost because a lot of the formulas for polyprotic acids will be written in ways where all of the protons it can lose are going to be out in front, right? So like H2SO4 or H3PO4 would be some kind of quick examples of polyprotic acids. And you may even hear more specific, like someone might say like a diprotic acid. That means it just has 2 protons specifically, or a triprotic acid would have 3. Now, finding pH for polyprotic acids. Most of the time, it's actually no different than finding the pH of just a single, what we call like monoprotic acid, which has just 1 proton, which is kind of doing the same calculation we did for HF, like back kind of the first example of today. And the reason it's going to end up like that most of the time is going to have to do with what happens with Ka values for these polyprotic acids. Most of the time, for most, well, actually, I can actually be more specific than this. I can actually say, then this update changed things, so I have to figure out what stuff looks like again. So I can actually say for all polyprotic acids, they're going to have multiple Ka values, but each successive Ka value is going to get smaller, usually by a lot. Which if we think about for just a second, kind of makes some sense. If you take a proton off of an acid, what's left is negatively charged. So then if you're going to try to take another positive charge off of something that's negatively charged, it's going to be harder to do. So as a result, your Kas keep getting smaller and smaller kind of for each proton that you're basically trying to take off. And so the trend is for all polyprotic acids, each successive Ka gets smaller. And in addition to this, if your second and or third Ka values are 3 powers of 10 or more smaller than the original one, you can basically ignore them in terms of pH. Which is kind of similar to the exasmall approximation, and it's kind of really what this is just another exasmall approximation to an extent. So if the second or third Ka values are 3 powers of 10 smaller than the first Ka, they can be ignored for pH. And again, the reason for that is as your Ka keeps getting smaller, that means it's going to dissociate less. And there's actually one extra piece to this. The way we would solve it if we couldn't ignore kind of like second or third dissociations is you'd basically have to do an ice table for every Ka. But what would end up happening is instead of having an ice table, I go back to kind of our first one that looks like this for dealing with an acid. Once you've done one dissociation, your starting concentration of H3O plus over here would no longer be 0. It would be whatever you ended the first ice table with. And if you now have something on the product side, thinking back to like the Chatelier's principle things, that means it's not going to go as far forward as it normally would, so it dissociates even less. So you have a smaller Ka that's going to dissociate even less than normal, which means you just don't even really get much H3O plus from that at all compared to what you get from just the first dissociation. So in terms of pH, polyprotic acids, the nice thing is pretty much only ever depends on the first Ka value. The only exception that I can think of is sulfuric acid. So I'll talk about sulfuric kind of specifically because it's kind of in its own little world for these. So sulfuric acid, what do we know about sulfuric acid in general? What kind of acid is it that when we talked about them before? It's actually one of our 6 strong acids, but it's only strong for the first dissociation. The second one actually does have a Ka value. So if you look up like Ka values in a table, you will see sulfuric acid there. Probably isn't going to have like a Ka1 because it's effectively infinite at that point. But it will have a Ka2 for losing the second proton. And it actually is still pretty big. It's like 10 to the minus 1 or 10 to the minus 2 for a Ka, which is kind of annoying because if that's how big the Ka is, it means X is small doesn't really work for it. So sulfuric is kind of the one exception to a lot of the polyprotic things I think that we see, that we do have to kind of take it into account for both dissociations. But that's just because the first one's completely strong. And on top of that, the second one, the K is so big, you kind of have to do quadratics, which usually means I'm not mean enough to ask about sulfuric like on an exam or something like that. But it is something I'd like people to at least be kind of like aware of. If the Ka value is big enough, you may have to do a quadratic, but honestly, most of the acids we encounter aren't like their Kas are small enough that we usually don't have to worry about it. Now, if your initial concentrations are low enough, maybe we do, right? So going back to like that HF example we started with for the day, like its Ka value was like 10 to the minus 4th, but if our initial concentrations were like 10 to the minus 2nd or 3rd, now we would actually have to end up doing a quadratic for that. Most of the time, that's not something we usually see for most of these. Like I said, like most of the things, chapter 16, 17, X small approximation is going to work on like 99% of the things we see and make our life a lot easier. All right. So with all that kind of said, if we'd take a look at just kind of a quick example here then. So I think the next example on active is carbonic acid. K1 is 4.3 times 10 to the minus 6. K2 is 5.11, and it wants to know what's the pH of a 0.47 molar solution of carbonic acid. Well, if we're looking at those two Ka values, they're 4 powers of 10 different. So you pretty much just figure out what's the concentration from the first association. That's it. You can use that to find pH. Because even if we did a second ice table, the amount of H3O plus extra it would give us is going to be so small, it's not even going to change the pH to how many sig figs you're trying to find. In this case, probably just 2 because everything here has 2 sig figs. So if I do want to find then the pH of this solution, even if for just the first association, what am I going to do for kind of initial setup? If I have a Ka value, that means it's a weak acid. So ice table is going to be the starting point still. So I'm going to write this right. So I have H2CO3. K1 is 4.3 times 10 to the minus 7th. I'm just going to write down the information before I swap my screen. 2, and this is 0.47 molar for a concentration. So what is my reaction going to look like for my ice table? Because again, I think the ice tables themselves aren't usually hard to fill out, and the math involved in them, especially if we don't do quadratic, is not usually too bad. But the tricky part of kind of all of this chapter, and particularly 17, as we start getting into more than one thing in the solution, is just writing the reactions, what's going on. Right, so this is kind of all of our starting information. No, why did it not? Why did it not carry over? Weird. Let's try one more time. There it goes. Don't know why I did that the first time. So there's all our starting information. So starting point, we said as soon as we have Ka or Kb, pretty much going to have an ice table. Generically, for any acid, we're doing Ka. It's the acid plus water, making H3O plus in the conjugate. In this case, we actually know the formula of the acids. You can say H2CO3 plus water. And since it's a Ka, we know we have to be making H3O plus as one product. And then once we take one proton off of carbonic acid, we now have HCO3 minus, right, is what we would make. But the rest of this should look pretty familiar. We have an initial concentration, 0.47. We can ignore the water component of this. H3O plus, we have none. HCO3 minus, we have none. Notice reaction has to go forward, so minus X plus X plus X. So filling out this table looks pretty repetitive for things we've kind of been doing for some of our other examples already. And now if I have the Ka value, no, it's covered up there. 4.1 times 10 to the minus 7th is my Ka1. So that means that Ka1, 4.3 times 10 to the minus 7th should equal x squared over 0.47 minus x. Right. Everyone okay with everything to that point? So that looks pretty similar to what we've been doing. Yeah, if you wanted to show it as HA plus water going to H2O plus plus A minus, that's fine. Especially because we're only doing we're only going to need to do the one protonation. I'm going to show it like I showed it this way just because I'm going to show if we had to do a second ice table, what would it look like? But then just kind of summarize why we were able to kind of skip it. So I can then, if in this case, 10 to the minus 7th, it's a lot smaller than 0.47, right? So we should be able to use x is small, ignore the minus x, to make this a lot easier to solve for our x in this case. And x is our H3O plus concentration here. And so that's going to be equal to 4.3 times 10 to the minus 7th times 0.47, and then taking the square root of all of that. So 0.47 times 4.3 times 10 to the minus 7th. Taking the square root of it. Looks like we get about 4.50 times 10 to the minus 4th would be our H3O plus concentration. And now if I want pH, I can take just the negative log of that. And we get about 3.347, or I think we had 2 sig figs most of the way through, so about 3.35. And if we had a situation where for some reason our Ka2 was actually pretty close to Ka1, what we would basically do to kind of keep going is that once this first association is done, there would be a second association that starts with HCO3 minus as kind of your starting acid, plus water making H3O plus, and now carbonate, CO3 2 minus. And I'll show that just really, really quickly here. So this would be the second association that could happen. And the part here that's different for this ice table, if we had to do it, is for your initial concentrations. Well, H3O plus and HCO3 minus both had X as what we got out of that first ice table. So 4.50 times 10 to the minus 4th would be the HCO3 concentration, but it's also the H3O plus concentration when we go to put things in. So that does change the actual kind of ice table setup that we have something on the product side. We still have 0 of one of our products, so we would still be going in the forward direction. You could fill out the ice table kind of from here. And you actually do get something kind of interesting if you kind of go through and do that, because if you can use the X is small approximation here, you actually end up with basically, I'll just show it real quick. What ends up happening is, since these two initial concentrations are equal to each other, if we actually do the X is small approximation for Ka2, the equation would look like 4.50 times 10 to the minus 4th plus X times X, all divided by 4.50 times 10 to the minus 4th minus X. But if we get to do X is small, the plus X and the minus X get ignored. And then this 4.5 times 10 to the minus 4th on top and bottom would cancel, and X just equals Ka2. That's it. It turns out that's pretty much how it works for all of your like second associations. It's like the actual X amount that you're going to solve for in those tables would just be Ka2. We just usually don't have to do this because if Ka2, we go way back up and see its value, Ka2 is 5.6 times 10 to the minus 11. If I take that number and add to 4.50 times 10 to the minus 4th that I got from the first association, do I even notice this number change? No, it's not a big enough value to matter. That's why we don't really have to do those second ice tables at all for any of these polyproducts when the Kas are very different. Right. So for us, really, we pretty much could have stopped here after that first ice table. And that's why we don't really have to do the successive ones. It's not going to change the pH in any way. So really for us, when we see these polyproduct problems, it's probably still most of the time going to ask for like, what is the pH? If that's all it's asking for, we can just do the first ice table. Don't really need to do more. The only reason we'd really need to do the second ice table is if it did something like ask, what is the concentration of the carbonate, like in this case. That's not something we can get from just the first association. We'd have to do the second ice table to find that. And that would basically be the X out of the second ice table. So there we actually have to go through some extra steps. The nice thing and kind of a quick trick that if you're taking like an ACS exam or something like that, that's multiple choice. If you ever have, like you're trying to find like the second anion in any of these equilibria, the second anion concentration just equals the second Ka value every time. Like we're not going to see any variation on that. And so that can be kind of like if you're trying to do something like a timed ACS exam, it's multiple choice. If you see the Ka2 value listed as one of your options for like the -2 anion that's been deprotonated twice, like those two things should match, like the concentration. Yes, that's being multiplied. That's from the carbonate here. Like that's this X. Because we had, for their initial amounts, we had to carry down what we got out of the first ice table. We basically had to do like back-to-back ice tables for like the second association. Because like none of the second protons can come off unless the first one's already come off. So you basically do the first association. So these are basically like two ice tables like back-to-back. So this is like the first one that we started with. We found this X value, which is H3O plus, but it's also the HCO3 minus concentration. So that when we go to the second deprotonation, we have the HCO3 minus concentration, but there's already some H3O plus from the first association there. Normally, that's not the case. Yes, yeah. All right. So questions at all and kind of seeing this with polyproducts? Like I said, most of the time, we're probably just going to be finding pH, which means we can just do the first ice table. That's it. All right. I think that wraps up most of the calculation side of chapter 16. We have kind of two other, like I think, general topics, though, that I do want to talk a little bit about. So we'll start talking a little bit about those, and then we'll move into kind of chapter 17 a little more in the second half. So we're going to start by talking about acid-base properties of salts. And really the goal of this is just to be able to figure out, like, if you have a salt and you put it in water, is kind of your resulting solution going to be acidic or basic? You can potentially do calculations with these. We're not going to do that in this class. We'll do that for other classes if we need to do those things. But for our main goal here is just identifying, like, if I take a general salt, let's say I take something like sodium fluoride and I put it in water, is my resulting solution going to be acidic, basic, or neutral? Is the other possibility or option. So how we go about doing this is, for your salt, you basically need to look at each ion on its own and figure out its relative kind of pH effects. And the way we do this is really by looking at conjugates. And it sounds kind of weird to kind of think about it first, but I think once you have a couple examples, it ends up not being too terribly bad to kind of go through. And so if I break this compound up to its ions, I have sodium plus and F minus. So I'm going to start with the anion because I think that's the easier one to look and figure out what the conjugates are. Because for the most part, your conjugates of any anion, you're just adding a proton. That's how you get to the conjugate, right? So F minus, its conjugate would be HF. So what do we know about HF in terms of relative strength, like strong acid, weak acid? HF is a I know this goes back to kind of the strong S list we talked about yesterday. I'm not a big fan of memorization, but that's probably one that we do kind of have to know. Like HF is actually a weak acid. It's the only halogen over there that makes a weak acid. We'll actually talk about some strength trends here in just a little bit too that'll help with that, I think. But since HF is a weak acid, what does that mean about F minus in terms of its relative strength as a base? Do you remember how we talked about how those things paired yesterday? Not a strong base, but it is a base. It's also going to be basically what happens is weak pairs with weak in terms of like relative sense. So if HF is a weak acid, F minus has to be a weak base. That's how we actually get an equilibrium that can go forward and backwards. Strong always pairs with something that is neutral instead. And we'll actually see that for our other ion here. For metal ions, if you have a metal cation in these ionic compounds, we basically pair it with hydroxide. And we look at, does it make a strong base or a weak base with the hydroxide? So in AOH, any group 1 metal is always going to make strong bases. So this is a strong base. But remember, since strong bases completely dissociate, that means they can't really go backwards. That means sodium by itself is effectively neutral. And that's kind of how your pairings are going to kind of end up working. If the conjugate is strong, then whatever ion you're looking at to begin with was just neutral. If the conjugate was weak, then your starting ion you were looking at was also weak of its type. And so our in kind of possibilities here, your anion is either going to be neutral or basic. Your cation is either going to be neutral or acidic. And then you're just looking at what happens if we put those things together. And so in this case, we have a weak base as an anion and a neutral cation. So that means this thing as a whole should be basic. So we'll look at kind of some of our different combinations there. You have the possibility of like both ions being neutral, which is how you could have a neutral salt overall. You could have just the basic anion and a neutral cation like this is how you'd get basic. You can have an acidic cation and a neutral anion would give you an acidic salt. And you do have the possibility of having an acidic cation and a basic anion. That can happen. If it does, you basically just need to look at your Ka and Kb values and figure out which one is bigger. If the Ka is bigger, it's acidic. If the Kb is bigger, it's basic, would be kind of the results of that. And so for instance, let's take a look at just actually a quick example for that one. Let's say we do, be a good example for this. Let's do ammonium fluoride. And we want to know, like, is this acidic or is this basic? So how this would work and kind of what we'll actually look at. Same thing, break it up to its ions. We have NH4 plus, and we have F minus. Again, the anion follows kind of our same pattern as before. Add a proton. So kind of the same idea, right? HF's a weak acid. That means F minus has to be a weak base. So we have a basic anion. Now, if we look at our cation, ammonium is weird because it's kind of the only polyatomic cation that we have. And because of that, its conjugate is not really adding hydroxide. Its conjugate is if it just loses a proton. It can actually make ammonia. NH3 would be its conjugate. Every other cation you pretty much see is almost always going to be a metal ion. Or it might be some kind of something that looks very similar to these, but one of the hydrogens is replaced with like a bunch of like, a hydrocarbon chain of some kind would be another possibility. But in this case, what do we know about ammonia in H3? What did we say about it yesterday? Yeah, it's probably like the classic weak base. It's like the most generic weak base that gets thrown in all sorts of different examples. So that one is definitely knowing that it's worth knowing that it's just a weak base. And really, anytime you have a neutral nitrogen compound like that, you can probably guess that it's a weak base. If nitrogen is there and it has a lone pair, pretty much can always be a weak base. Now, if the ammonia is a weak base, what does that mean about ammonium in H4 plus? Similar to the right side, if weak pairs with weak, that means ammonium is a weak acid. So if we run into this situation, we need to compare Ka and Kb. And ideally what we want is Kb for, oops. We need the Kb for F minus, and we need the Ka for NH4 plus. Now, the annoying part of trying to make this comparison is when you go to look at Ka and Kb tables a lot of times, you're not going to find a Kb value probably for F minus in any table. What you will find probably is Ka for HF is 6.8 times 10 to the minus fourth from one of the examples we saw earlier today. Likewise, if you look in a table of Ka values, you probably won't find ammonium, but you will find a Kb for ammonia in a lot of those tables that have Kb values, which is about 1.8 times 10 to the minus 5. The problem is that's not really the Ka and Kb of our base and acid. We have a Ka of an acid, but we really want Kb of F minus, right? We have Kb for NH3, but what we really want is Ka of NH4 plus. How would we get the Ka and Kb of the things we want? There was one other equation we mentioned kind of almost in passing yesterday that we didn't really do it. So it has to actually do with Kw. Kw is equal to Ka times Kb for conjugate pairs. So that means if I have Ka for HF, I can find the Kb of F minus by taking Kw divided by the Ka of HF. Right? Likewise, if I want the Ka for ammonium, I can take Kw divided by the Kb of ammonia and get now my Ka value I want. Now, the nice thing about this, it's annoying I'm going to have that extra step, but I think you'll see the pattern here real quick once I show it. So Kb for F minus is going to equal Kw over Ka of, I'm just going to write of HF there. So 1.0 times 10 to the minus 14th is Kw, divided by that Ka I just wrote above, 6.8 times 10 to the minus 4th. And I'll get that value in just a second. Same thing, I can get the Ka then for ammonium, NH4 plus, Kw over the Kb of ammonia, which will be, again, 1.0 times 10 to the minus 14th, divided by 1.8 times 10 to the minus 5. And I'm pretty sure that's like 2.1 times 10 to the minus 10th, I think. I think this other one's going to be something, well, that one I might have to actually punch. Can't recognize that one right away. Oh, that's, let's try it one more time. All sorts of problems entering stuff. There we go. Okay, so there we get about 1.47 times 10 to the minus 11th. And now we have the Kb and the Ka that we can compare. But if we're looking at them, the Ka is slightly bigger. Now, something that can just be time saving, Ka is bigger here in the actual for the ions that we cared about. But you'll also notice that Ka was bigger for the things they gave us that were the conjugates. If Ka was bigger initially, Ka is going to be bigger on the conjugates as well. And so that can kind of save some comparison or save some converted time, where if you're given a Ka and Kb, even if they aren't for the exact things you wanted, if they're the opposites, the same trend's going to hold. Ka is still going to be bigger. So since Ka is bigger for our initial compound, this H4F, since Ka is bigger than Kb, it's acidic. That's about as hard as any of these problems would ever be. They can't get any harder basically than that for these salts. Probably 8 times out of 10 or more, you're only going to have like either an acidic cation or a basic anion, and then it's that one is paired with something probably that's neutral, or they're both neutral, and it's just an easier process than to figure out what your salt is. Right. I think this is probably a good spot to take kind of a short break, and so we can come back and take a look at just kind of a couple of quick comparisons with salts as far as being acidic or basic, some quick acid-base trends, and then we'll jump into kind of the start of chapter 17 with some mixtures of things. But let's take about 35 after. It's going to be a break, so 4 or 5 minutes here, and then we'll get started back up again. All right, so we'll start back up, I think, here again. So kind of see like the salt kind of acidity and basicity show up for ways and kind of basically for these different salts listed A through D, would we expect to have a pH greater than 7? So if I need a pH greater than 7, that means I need a basic salt of some kind, right? So what I'm looking for then is, of these salts, which one is going to be basic? There's a couple different ways to kind of go through and try and process that. The first, though, I would kind of encourage is you need if you're going to have a basic salt, the anion has to be basic. So with that in mind, I've written down kind of what our 4 salts are here. I'll come back to this table, but for now, I'm just going to look at each of these compounds kind of individually. And so for the first one, ammonium bromide. If my anion is bromine a basic anion? Well, if we think about it in the way we had for kind of our previous examples, the conjugate of bromide would be what? Let's see if this catches up. It's light. There it goes. So breaking this thing into its ions, I'd have ammonium and I'd have bromide, but bromide's conjugate would be HBr. Right? What do we know about HBr? Yeah, that is a strong acid. Right? Basically HCl going down the rest of the halogens like HCl, HI, all of those are strong acids. HAT would be if astatine was common enough to ever make that, but it's not. So HBr, it is a strong acid. Now, what does that mean then about bromide as an ion? Is it basic? No, it's actually just neutral. Right? The conjugate of something that's strong in terms of pH is basically just neutral. So without even looking at the cation, if my anion's neutral, is there any way this whole salt can be basic? No, not really. So this actually, and really we've already looked at ammonium. Ammonium's a weak acid, right? It's the conjugate of ammonia, which is a weak base. Really, this first salt, if anything, is acidic. The second salt, look at what the anion is. It's bromine again, or bromide. If bromide's the anion, can that be basic? No, same thing. So can't be basic. Right? Same pairing that we just saw. All right, what about the third one then? Calcium nitrate. So we have calcium, and then we have the nitrate ion. All right, nitrate. What's its conjugate? We add a proton to it, comes HNO3, which is nitric acid. What do we know about nitric acid? It's also one of our strong acids. So if that's strong, that again means that nitrate is neutral. So if nitrate's neutral, can't be a basic salt if the anion's neutral. So really we're only left with one other option here, this very last one. Now this one's written admittedly in a little bit of a weird order. Right? It wrote sodium at the end, but sodium is the cation here. And the anion is the C6H5COO minus, which this COO ending like this is a pretty common, it's something called a carboxylate group. If you go on to take organic chemistry, you don't really need to know that for right now. But whenever you see that, there's another polyatomic anion that we do see that's very similar. It's acetate, which acetate is CH3COO minus. It's a really similar ion. And one of the trends that we're going to see pop up a bunch is that acetate or anything really that ends in that COO minus, their conjugates would still be to add a proton. But for say like acetate, when I added a proton, is acetic acid a strong acid? It wasn't one of those main 6 we talked about. So anything that ends with like that COO minus like this as an anion, when you add the proton, it doesn't make a strong acid, it makes a weak acid. So really this thing's conjugate, if I want to be particular about it, I could just say C6H5COO, and then I'll add. The reason that this one doesn't list the hydrogen first is sometimes you have kind of those organic chunks or chains at the beginning. They'll put the hydrogen at the very end next to the oxygen that it's attached to try and show structurally what's going on. So it's the only time hydrogen's not listed first in kind of like the acid formulas is when that happens. But adding this hydrogen, it's not a strong acid, so this must be a weak acid, which means that this is a weak base. So there's our basic anion that we've been looking for. But we should still look at the cation that it's paired with. And we see sodium, group 1 metal. Pretty much all of our group 1 metals, they're always going to be neutral. because they're going to make a strong base with the hydroxide. So the individual group 1 metals themselves are always neutral. And really group 1 metals, for pretty much everything we do in chapters 16 and 17, they're kind of just spectator ions. They're convenient cations to help make like a solid ionic compound for an anion that we want to use probably for something else. That's why we use them all the time. Put them in solution, group 1 metals, they never do anything. And a lot of the times you can even kind of ignore them, as we'll see and start to talk about reactions here in a few minutes. So in this case, the only one of our options then that could have given us a basic salt would have been this last one. Right? The sodium would have been the neutral cation, and we do have a weak base anion that has that COO, kind of like what we call carboxylate group there at the end. And another thing that can help with that, if I look, here is in this table, C6H5COO with an H has a Ka value right here. The table is trying to tell us that this thing is a weak acid, so that when we take that hydrogen off, that means its conjugate must be a weak base. Would be kind of the trend that we would see. All right. So the last part of kind of chapter 16 for comparisons, and this is also going to be mostly qualitative. This is going to have to do with kind of acid strength trends. So we can just compare relative acid strengths really just from formulas. And so how this works, it is going to depend on the type of acid we're looking at, because there's slightly differing trends for binary versus oxy acids. And it's not going to be really possible to take binary and oxy acids and directly compare. It's not something we're going to really be able to do. But if we have 2 binary acids, we usually can compare their relative strengths based on one of 2 trends. And that is that as we go across a row to the right, our acid strength gets higher. So as you move to the right, and when I say moving right, I mean on the periodic table, this is going to lead to stronger acids. And the reason for that is as you move to the right, what happens to the electronegativity of the elements? It goes up, right? So the more electronegative those elements are getting, that means it's making a more polar bond to the hydrogen. And the more polar that bond is, the easier it is then to break an H plus off of that bond. And so the more polar the bond, usually the stronger the acid. It's kind of the general trend. Now, that does conflict slightly with if we go up and down. So if we're moving down the periodic table, even though things are getting less electronegative and the bond is getting less polar, it actually still makes a stronger acid. So up here, I'm going to put kind of the explanation for this top trend is really polarity. But the explanation for this second trend for moving down a periodic table, making things stronger, this has to do with bond strength. As you move down the periodic table, what happens to the size of all those atoms? Yeah, they start getting bigger and bigger, right? So at the point where you get down to say like where iodine is in the periodic table, iodine is this huge, big atom. If it's trying to bind to a little tiny hydrogen, how well do the size of those orbitals match up to actually overlap? Not really well. So the bond ends up actually just very weak. Even though the bond is not very polar, the bond itself is very weak because the orbital overlap is not very, like the size mismatch is just too much. And so the size mismatch makes the bonds much weaker as we go down. And the weaker the bonds get, the easier it is to break the bonds to then make the acid as a result. And so those are kind of the 2 trends we see with binary acids. As we move to the right, acids get stronger because the bonds get more polar. As we move down, because as the atoms get bigger, they make weaker bonds to hydrogen. Yeah, acids get stronger as well. So acid strength goes up as we go to the right, down for binary. And then for our oxy acids, there's kind of 2 possible ways to compare these. One is if you have the same central element, but different numbers of oxygens. So same central element. The trend that we're going to see for this is the more oxygens we have, the stronger the acid. And we've actually seen this a little bit before. Like for instance, HNO3, we know is a strong acid. HNO2 is not. It's actually a weak acid. Right? That's kind of a very quick example of this. Now, in terms of why that is, this is mainly due to resonance. And this is something that I'll actually, like, again, people going on to take organic chemistry will probably see this a lot. If I draw Lewis structures for each of these just real quick, for nitrate, it's going to look something like this. So this would be the Lewis structure of just just NO3 minus by itself. But when I draw it like this, I have a resonance where that double bond could really be spread between any of those three spots, right? I could have put the double bond here or here as well, same thing. If I look at the Lewis structure for NO2 minus, nitrite, it looks like this. It also has resonance. The double bond could be to either side, but the way the resonance kind of takes place here is the more places you can spread kind of that double bond or spread your different negative charges, the more stable that ion becomes. And the more stable your ion is, the easier it is for the proton to just leave, and then you can still have that anion be there and be stable. And so the end kind of trend, when I say like resonance is the driving force here, more resonance leads to the stronger acids. The more resonance kind of possibilities you have, the more places you can move those double bonds, the stronger the acid's going to be, because the resonance helps make the ion that gets kind of left behind more stable. And I think there's that viewpoint, like the more chemistry you take becomes a lot more important. Like organic chemistry, we'll talk a lot about like leaving groups and kind of like what things get left behind and the relative stability of certain ions. And resonance plays a huge role, that the more resonance you have, the more stable a particular ion is, and that helps explain a lot of patterns for certain reactions. And in our case for acid strength, the more resonance we have, the stronger the acids get. Right? Like H2SO4 is another example of a strong acid because it has a lot of resonance that's present in it. Now, the other trend for oxyacids are if we have different central elements but the same number of oxygens. And in this case, the more electronegative central atom will always be the stronger acid. And this basically just goes back to polarity again. The more electronegative your central atom is, the oxygens that are kind of all around it can't pull many electrons from the central atom, so instead they pull that much extra electron density from the hydrogen. It makes the hydrogen bond more polar, and the more polar that hydrogen bond gets, the easier it is to break that hydrogen off and then have your acidic proton. So trend-wise, the kind of application of this, I think the description of it almost sounds more complicated than anything. But if you have two polyprotic acids, bless you, let's say we compared H2SO4 versus H2SeO4. And want to know which of these is the stronger acid? Well, they have the same number of oxygens. Your central atom is different in each of them. The one that's more electronegative between sulfur and selenium would be, based on the periodic table, should be sulfur, right? Sulfur's above selenium on the periodic, directly above it on the periodic table. So if sulfur is more electronegative, it should then make the stronger acid, because oxygen can't pull as many electrons from the sulfur. It'll pull more from the hydrogen, which will make it easier to break that hydrogen bond to make the acid itself. And I'll give kind of a visual aspect of this as well, because the actual protons that are being lost from like sulfuric acid are attached to the oxygen, right? So if this bond here, if the oxygen can't pull many electrons from the sulfur, the oxygen is going to pull a lot more electrons from the hydrogen in terms of the dipole it kind of creates. Let's see if I can make something resembling a dipole a little cleaner than that. Makes a bigger dipole, kind of pulling electrons from the hydrogen. And that makes it easier for basically that proton to just be lost, which is kind of what it means to be a stronger acid, is to lose that proton easier. Whereas if I have selenium, the oxygen is going to be able to pull more electrons from the selenium. So the dipole from the hydrogen is a lot smaller. And so that hydrogen gets held onto a little bit tighter. It's actually a little bit harder to break that bond. It's kind of the pattern. They refer to this as an induction effect or inductive effect. I think that's probably more than we really need to know for this. I think the general pattern's not too bad. The more electronegative your central atom gets, the end result is a more polar bond to the hydrogen, becomes a stronger acid. The general. Yes. This is the trend for that situation. Oh, okay. So that if you have the same number of oxygens, kind of like these two examples here, if you have the same number of oxygens but the central atom is different, whichever central atom is more electronegative should make the stronger acid. That's the general trend, and there won't really be the exceptions to that. Your other oxyacid trend. So I think that the easiest thing to do is just look at some very quick kind of comparisons. So things we would have to, and this is, we'll probably already guessed, like greater than less than equal to questions fit this kind of stuff really easily. Where you can have something like we can compare, say, we already looked at HNO3. So if we had something, let's say like H2CO3 versus, what can I do? H2SiO3. And I want to know which of these is a stronger acid. Same number of oxygens, different central atoms. So as a result, what I would expect in this case is that carbon being more electronegative than silicon, I'd expect this to be the stronger acid because the carbon's more electronegative. If I have things with different numbers of oxygens, so let's say HClO3 versus HClO2, same central atom, different number of oxygens. Really the trend here is the more oxygens you get, the more resonance that always exists. So I'd expect more oxygens to be the stronger acid for those comparisons. Right. But I would never end up comparing, say, like HClO2 to like H2SiO3. Like there's not enough in common. Like they either have to have the same central atom or the same number of oxygens for us to easily compare. Otherwise, that comparison gets a little bit too murky for us to make without more information. So we can take a quick peek at, I think, a couple quick examples of this, and then we'll kind of wrap up the last bit of this chapter. So here, wants to know if we have a list of 4 different acids, just which one will be the strongest? Well, all of these have the same central element. It's all iodine. So which one would be the strongest acid? And the one that's got the most oxygens, HiO4. That should be the strongest acid. So easy enough, I think, pattern to remember for those. Here, want to know which is the strongest acid? These are all binary acids. And these are all going basically down a column. So as we go down a column, what's our trend for moving down a column for acid strength? The acids get stronger as we go down, because as those elements get bigger, the bond to hydrogen gets weaker, which makes it a stronger acid because it breaks it easier. So in this case, the one that's farthest down, I believe, is tellurium. So H2Te, the strongest of those. And that is a trend that also helps explain, like when we get to the halogens, HF was not a strong acid, but everything below it was, right? Because as we keep going down, they do get stronger. HCl is, HBr is an actual stronger acid than HCl. HI is a stronger acid than HBr, even though all of them are strong. We can still kind of characterize their strengths relative to each other, and that trend actually does still kind of hold true. All right, one very last piece then for chapter 16 before we start getting into kind of mixtures of things here. And this is just what it means for a proton to be acidic in the first place. And something I think that is also useful to anyone taking kind of chemistry beyond this class, particularly organic. So identifying acidic protons. If we have a chemical structure, the main requirement is we really need polar bond to the hydrogen. If we don't have a really truly polar bond to the hydrogen, usually the hydrogen is not very acidic. And so some quick kind of visual examples of this. Here's a compound that has a bunch of hydrogens. But there's only one acidic proton in that compound. And that's this one. That one's acidic because it's a polar bond being attached to that oxygen. The other hydrogens are not acidic because those are all pretty much non-polar bonds to a carbon. Right? This is why this is actually acetic acid that we're looking at. That's acetic acid structure. And it's why acetic acid is a monoprotic acid. It only has one proton it can lose. Right? And it's why you'll sometimes active in particular will write acetic acid's formula like this, even though I'm not a huge fan of necessarily writing it this way. But there's more than one hydrogen, but only one's written out front because that's the only one that's actually acidic when it's written out. Likewise, turns out, and this is just kind of a weird case. Let me draw this one. So, oops. This is the relative structure of phosphorus acid, this is H3PO3, which from that formula, the way it's written, you might think it should have 3 protons that can come off. But it turns out this is the thing's actual Lewis structure. It actually can only lose 2 protons, which are these 2. The one that's attached to a phosphorus, turns out phosphorus and hydrogen also have about the same electronegativities. It's not really a polar bond, so that hydrogen doesn't really come off, right? So these would be the acidic protons. So your main key is for a proton to be acidic, you usually want it bound to something that's fairly electronegative. More often than not, probably an oxygen in a lot of the examples that we see, or maybe like a nitrogen or something of that sort that has a positive charge in particular would also make for usually good acids. But that's something I think that's useful, particularly kind of like down the road, like organic chemistry type things, like hydrogen's attached to a carbon or some other element that's kind of around carbon and similar like electronegativities. Those aren't really acidic protons that are easy to come off. There are some other unique things we can do with like some double bonds and think compounds called alkenes to potentially make carbon hydrogen bonds acidic. But for the most part, they're not just like a standard compound like what we're used to seeing here in Gen Chem. Carbon hydrogen bond, it's not going to be acidic in any way as we see them. All right. So I think that wraps up all of chapter 16. So I want a little bit of time to talk about kind of the very start of chapter 17. And really chapter 17 has a lot of different things in it, but our focus for at least this early part is really just going to be looking at pH of mixtures. Right? In chapter 16, all these examples we had that were like, calculate the pH of this solution, all had one compound in it. Now we want to look at what happens if we have multiple compounds in that solution. And we have kind of a couple different possibilities. And so I'm going to highlight kind of each of the possibilities just kind of relatively quickly first. But we could have basically an acid plus an acid, or a base plus a base would be like one combination. And I kind of group these together because if you have 2 acids and put them together, an acid doesn't really react with an acid. Likewise, a base doesn't really react with a base. And so in each of these instances, probably what's important is we really only care about what is strong in these types of combinations, which means if I have a strong acid and a weak acid all in the same solution, I pretty much just ignore the weak one, because there's no way that weak acid is going to give off as much H plus or H3O plus as the strong acid in an amount that's going to change kind of our actual pH. So if you have a strong acid and a weak acid, you basically just calculate the pH of the strong acid and that's it. Like the weak acid is never going to give enough to really matter. The only time that might not be true is if your concentration of the weak acid is like 1,000 or 10,000 times bigger, but we're not likely to really run into situations like that in here. Same thing would apply to bases. If you have a strong base and a weak base, pretty much just find the pH of the strong base. That's all that really matters. So strong plus weak, pretty much, I'll highlight that here. Strong plus weak, we ignore the weak. And that applies to if it's two of the same thing. Right? If it's an acid and a base that we're mixing, it's going to be totally different. We'll get to that kind of in a second. The other possibility for these acid-acid or base-base combinations is if we have both of them being strong. So if I have a strong acid mixed with a different strong acid, in this case, we need to really find the moles of H3O plus, and then we can find the concentration of H3O plus, and then we can find kind of the pH, is kind of the three general steps that you can go through. Because if you know the concentration of your strong acids, those basically are the concentrations of H3O plus, but it kind of depends, like if it's all one solution and you just know the concentration of each, you can add them together. But sometimes it'll be like, you have 10 milliliters of this 1 molar acid, 5 milliliters of this 1.5 molar acid, you put them together. You kind of have to figure out what's the moles of each that you're putting together, find the total moles of H3O plus, divide by a total volume to get a concentration, and then you can get a pH. I don't think it's worth probably having to go into like full walkthroughs of those because we don't encounter those situations as often. I think they're a lot less common typically. What is going to be more common, so this, I'll highlight this as kind of a possibility one of what can happen when we have a mixture of things. Possibility two is we can actually have a conjugate acid-base pair. Right, so what does it mean to be a conjugate acid-base pair again? It means we have two compounds that differ in their formulas by exactly one proton. So we were talking about conjugates before, so something like NH3 and NH4 plus. And I'll put up here, it must be weak for this to really work. So if you have an conjugate acid-base pair and one is strong, the other is neutral, so you just find the pH of the strong thing and that's it. You don't have to do anything else. But if we have a conjugate acid-base pair together, if we think about this, I have an acid and a base, but what's unique about having a conjugate acid and base together is normally acids and bases want to react with each other. But the problem is if I react these two things with one another for like an acid-base reaction, usually all an acid-base reaction does is move a proton around. But if I take a proton off of NH4 plus and put it on NH3, I just make NH4 plus and NH3 again. I didn't change anything. Nothing really happened. And that's what's kind of unique about these types of situations, is if you have both kind of halves of your conjugate pair, this is when you actually create something called a buffer solution. How many people have heard that term buffer solution before? You're taking biology labs, especially upper level ones. Probably most things you do are in buffer solutions. Does anyone know what the purpose of a buffer is and why they're useful? The reason buffers are useful is they're very resistant to pH change. Which is important because most biological systems, if the pH changes too much, like a lot of different protein structures and other things might break down if the pH is in the right range. And if the protein structure breaks down, it doesn't work anymore, and also the biological function goes haywire. So pH control is really crucial for most biological systems. And buffers, like for instance, even in us, our blood is actually a buffer system based around carbonic acid. And so it's meant to kind of regulate pH change to avoid getting too acidic or too basic to cause any of those protein structural issues. The way it does this is if I have a buffer that's this conjugate acid-base pair, I basically have an acid and a base already in my solution. So if I add a different acid, there's already a base there that can neutralize that acid we're adding. If I add a different base, there's already an acid there that can neutralize the base that gets added. And the end result is your pH doesn't change very much. Whereas normally you add a little bit of any kind of strong acid or strong base, pH will change very drastically for just a normal solution. But to a buffer solution, you can add kind of strong acid, strong base. pH isn't going to be affected very much. And that's kind of the purpose or the usefulness of buffer solutions. And it turns out for a buffer solution, you can still do ice table type calculations, but there's just kind of a faster, easier way. There's something called a Henderson-Hasselbalch equation. To calculate pH for buffers. But it does only work for buffer solutions. And this equation is that the pH is going to equal pKa plus the log of the base concentration out of your conjugate acid-base pair divided by the acid concentration of that conjugate acid-base pair. And just to highlight pKa, if we have a P in front of something, what is that? What are we doing? P in front of something means we're doing the negative log, like for pH or pOH. So pKa, this is just the negative log of Ka. That's kind of how to think about that. So this is really useful where if we end up in a situation with two things in solution, but we recognize they're a buffer, we don't have to do any ice table. We don't have to do any BCA table stuff that we're about to talk about. Instead, we can jump straight to this equation. As long as we know the concentration of our base and our acid for the conjugate pair, we can just find the pH of that buffer solution. Right, it's fairly quick. Where we'll see this show up is probably less just immediately from like what they give us in a problem. And a lot of times this will be what we use after some kind of partial neutralization, which is kind of this last thing that we're going to talk about for our last situation for a mixture, which is if that we have an acid and a base that are not a conjugate pair. Because in this case, if you have an acid and a base together, they are going to do a neutralization reaction. And one of the things that's really important about neutralization reactions are that their equilibrium constants are enormous. We're talking like 10 to the 10th and bigger for most of them, which if we're talking about what that really means, if our equilibrium constant is huge, that means we pretty much only have products at the end. So in terms of calculations, we treat neutralization reactions as going to completion. And the highlight here that I'm going to make is that anytime we do a neutralization reaction, this is when we're going to use something called a BCA table. Ice tables are for equilibrium. BCA tables are for reactions that are going to go to completion, of which the big one that we see in this chapter is a neutralization reaction. So anytime we get an acid and a base, they're not a conjugate pair, they're going to undergo neutralization. We're basically going to treat it till it goes to completion, or treat it as it goes to completion. So I think the easiest thing to do for this last part is to give kind of an example. So I'm going to give just a quick example. I might do the active ones ever so slightly out of order here. That's okay. Yes, let's do 10. I'll skip and come back to 9 in a minute. All right, so here we're asked to calculate the pH when 20 milliliters of 0.150 molar KOH are mixed with 20.0 milliliters of 0.3 molar HBRO, and it gives us a Ka value. So this is basically kind of the new addition that we get from chapter 16. Chapter 16, we get a problem that's find the pH of one thing. Now we're trying to find the pH with multiple things. So the first and most important thing whenever we see situations like this where we have two compounds, we have to figure out what are those compounds. Are they acids? Are they bases? Are they strong? Are they weak? Do they make a conjugate pair? We have to kind of consider all of those possibilities. So in this case, just doing one at a time, KOH. What is KOH? Yeah, it's a strong base, right? All right, we're pairing this with HBRO, which would be what? And how do we know? It's an acid, and it's specifically a weak acid because there's a Ka value right there for it. All right, so I have a strong base and a weak acid. And most of the time, if you have something that's strong paired with something the opposite, whether it's strong or weak, That's our neutralization. It's going to react all the way to completion. So we are going to get a neutralization. These things are not a conjugate pair, right? And to give an idea for like conjugate pairs, right? This previous example, like here's NaCNO versus HCNO. Well, they both have this, like here is CNO as basically an anion that would be there, and HCNO, that would be a conjugate pair. That would make a buffer. That's not what's going on in this example that we're looking at, right? Those two compounds are very clearly different by more than a proton. So we are going to get a neutralization reaction for this. All right, the next step then is, if we're going to get a neutralization, what is that reaction going to look like? And this actually kind of goes all the way back to 1211 things to some extent. But if we do a neutralization, an acid plus a base, what are the usual products? And particularly if hydroxide is the base, one of the products will always be water, because OH is our base, plus the proton, OH minus plus H plus is H2O. That's where the water comes from. So if hydroxide is the base, which it is kind of in this case, we're going to get water as one product. And then usually you're going to have basically a combination of your other ions. So in this case, like potassium and the BRO minus would combine to make our salt product. So in Gen Chem 1, we probably talked about acid plus base making water to salt being probably kind of the most common form of a neutralization. That does only apply to hydroxides as bases for making the water part, because if you don't have a hydroxide as your base, you actually won't make water, you get something else. But for right now, we won't worry about that. We'll probably worry about that Thursday. But if I look at this example, for writing my reaction, I would basically write a reaction, and that is my HBRO, my acid. This actually screen swaps. There it goes. So I want writing my neutralization reaction. I don't know why it's still being so laggy. I would have HBRO plus, and a lot of the times, if it's a group 1 hydroxide, I just leave off that ion. Like the group 1 ion, it's a spectator ion. We said before, all of our group 1 ions in terms of pH are just neutral. So I just leave it out and just write this as OH minus. I think that just makes it easier to see conjugate pairs as we go through. And you'll notice that I drew a one-way arrow here, not my equilibrium arrows that I've been drawing, because this reaction is going to go to completion. And so product side here, we're going to make water. And for my remaining ion, because I left the potassium out, it's just BRO minus. It's the conjugate of that HBRO. Right. So there's my reaction. Now, for my BCA table, two things about this. It's very similar to an ice table, but instead of molarity for BCA tables, we actually specifically use moles. And that's to account for, we want the moles of the things that we're reacting to be involved. You can do molarity if everything is all in the same solution already, because then it will work out the same way. But if you have so in our case, for our example, we had 20 milliliters of 0.150 molar potassium hydroxide, 20 milliliters of 0.3 molar HBRO, like they're not mixed together yet. So we can't just use those concentrations. We really need the moles. If these were the concentrations and it was all in one solution already, we could use molarity, but it's not the case. Most of the time, it'll probably be similar to this. So we need to use the moles to actually do this calculation. So BCA tables, they need moles. That's one big difference from ice tables. And the other big difference is your change is not X. You don't have any X's that show up in this at all. Because if this reaction goes to completion, whichever of our two reactants we had less of to start, that's the amount that things are going to change. They're going to go until one reactant hits 0, basically, at the end. And so to get our pieces for this, we want things in moles, we'll find our moles of HBRO first. They told us that we had 0.300 molar and 20 milliliters. If I want to find the moles from that information, what would I do? Molarity is moles over liters. So if I multiply by the volume in liters instead of milliliters, I should get moles. So my moles of HBRO, it said it was 20 milliliters, right? So in liters, that would be 0.0200 liters, right? For its volume times the concentration, I think was 0.300. Is that right? That's moles per liter for the HBRO. So that'll get our moles of this, which looking at that real quick, I think is 0.006 or 6 times 10 to the minus 3. Just leave it as this though. So 0.00600. Then I want the same thing for moles of hydroxide. So our moles of hydroxide, its volume, I think was also 20 milliliters, right? But its concentration was 0.150, so half as much. So that would be then 0.00300 moles. So for my BCA table, I can now put the starting moles of everything in. And my change line is I'm going to look at those two amounts of my reactants to start with, because that B does stand for before in this case. C is still change, but the change is now whichever one of those is smaller, that's how much they should both be going down, right? So if I have 0.003 is the smaller of those, I'm going to subtract 0.003 from each of these, which will leave me 0.00300 for the HBRO, none of the hydroxide, and you should get at least one of the reactants is 0, and that kind of A or after line for these BCA tables. But for the product side, again, stoichiometry, at least the nice thing, everything's still 1-to-1 all the way through. So plus that number of moles on the product side. So I get 0.003 moles of BRO minus as well. All right. The hardest part of these problems where we do this neutralization is we go through all of this work in a BCA table, and then we still have to look at what's left, what's still there. And then figure out, it's almost kind of like starting at the beginning again of like what combination of things are left. Because if we started with a neutralization, the next step of kind of what's left is probably that you either have a buffer or you have like 2 acids, one of which is strong, or 2 bases, one of which is strong. And then you just find the pH at the strong thing. So in this case, what we need to look at is how do the 2 things that are left compare to one another? We have HBRO and BRO minus. Those are conjugates. So if I have conjugates that are present at the same time, that makes a buffer. So if the only 2 things left in my solution after the BCA table are those, since they're since they are a conjugate pair, we have a buffer solution. Now, the nice thing about this, if we have a buffer, we don't have to do any more tables. As soon as we recognize that it's a buffer, we can jump to this Henderson-Hasselbalch equation to find our pH. So we can use our equation here. pH equals pKa plus log of our base concentration over our acid concentration. And pKa, remember, is the negative log of the Ka. The problem did give us a Ka value for our acid. So Ka, they told us, was 2.5 times 10 to the minus 9. So negative log of 2.5 times 10 to the minus 9. That's our pKa part. And then plus the log of the base over acid concentrations. The nice thing for your BCA tables, that's for everything all in your one solution. Concentrations like moles over liters divided by moles over liters, but if it's all in the same volume of solution at the end, you can really just take moles over moles and it's the same thing, right? So we actually don't have to get the concentrations. We can use the moles from the BCA table for the concentrations here, and that's fine after we've done the BCA table. So it's okay to kind of go from moles to the concentrations for this step, but like previous, like starting molarities 2 moles for the BCA table, we really need the moles for that to work. And so in this case, the moles of our base from our BCA table, we had 0.03 of the BrO3 minus, divided by the moles of the acid, which were also 0.003. Right, kind of coming just back up to the table. So, and I will highlight in that equation for a buffer, it wants the moles of the base out of the conjugate pair, not the base that you started out with in the reaction. That is kind of something to pay attention to. Now, most of the time, unless there was already some of your conjugate base there, the moles of that base that you reacted are going to equal the moles of the conjugate base that you make. That should happen if you didn't have any conjugate base to start with. So there will be a correlation kind of between those two things, but you are specifically looking for the moles of your conjugate acid base pair that you're putting into the Hasselbalch equation. And now we have all the pieces to find our pH. So we can do the negative log of 2.5 times 10 to the minus 7. Which is, it's 2.5 to the minus 9, is that right? Okay. 2.5 to the minus 9 is 8.60. And then if I have 0.003 divided by 0.003, that's just 1. And the log of 1 is actually just 0. So that's actually it. That is my pH in this case. So I end up with a final pH then of about 8.60. Now, these are, I think, probably of all the things we do all semester, I think these are kind of some of the hardest problems that we really encounter. The only one that gets slightly harder, as we'll talk about on Thursday, is for titration specifically. If we're at equivalence points for strong, weak titrations, those get kind of ugly. It's basically all of this plus kind of one extra thing. But our end goal of what we want to be looking at when we have multiple things in a solution, figure out what each piece is, figure out your appropriate starting steps. If we do a BCA table like this, which is only for neutralization reactions, at the end of the BCA table, it's kind of almost like starting over. Look at what's there that's left. How do they compare? Do they make a buffer? Or really your kind of two main outcomes you normally see is you're either going to have a buffer, or you're probably going to have like a strong acid and a weak acid, or a strong base and a weak base. And in those cases, you just ignore the weak thing, find the pH of the strong thing that's kind of left over, and that'll be kind of how you actually get the pH of those solutions. Now, we do have just a little bit of time left, so I do want to look at one more example. Questions on this one that we went through, any of the pieces, before I take a look at that? So let me think what I will do is I'm going to go ahead and remove the very last question that's on this, just to get to that one. So we'll take a look at number 9 that I'd skipped previously. So here it asks, what is the pH of a buffer? So right away, it tells us this thing's a buffer solution. I will tell you right now, this is one instance where maybe I'm not as nice as active. I probably would not tell you that this is a buffer. I would just ask, what's the pH of a solution with these two things there? Because I want people to be able to pick out based on what's there for the compounds that we are looking at a buffer solution. So how do we figure that out? Well, let's look at what it tells us here. We have 0.220 moles of HCNO, gives us the Ka value, and 0.410 moles of NaCNO. So something I think that will be very helpful for finding conjugate pairs when we start having pairs of things. If you have a group 1 metal ion involved, or if you have a halide ion involved, I would almost just ignore those ions. The only halide I'd ever pay attention to is fluoride, because it is slightly basic. It can affect pH things. But chloride, bromide, iodide, they're all conjugates of strong acids, meaning they're just neutral ions. All of your group 1 metals are always neutral ions. If you have those ions, kind of ignore them and then compare formulas, right? Because looking at NaCNO with all of that compared to HCNO, those aren't different by just a proton. That sodium's there too, but as soon as you put this in water, that sodium goes away, right? And you have CNO minus and HCNO. That's very easy to see they're different by a proton, right? So I think the easiest thing that helps for finding conjugate pairs, ignore group 1 metals in these formulas. The only thing you'd ever need the group 1 metal there for is to find a molar mass if you need it. That would be it. And that I can tell you for at least tomorrow's exam, I probably wouldn't have something like that. Maybe for our last exam, exam 4, we'd have something like that could come up. And honestly, for ACS, they probably wouldn't have something quite that complicated because they just can't ask questions that long at that point. So really trying to identify what's going to happen. Do we have a buffer? Ignore your group 1 metals. I think it'll make it easier to pick things out. And now once you recognize that this is really just CNO minus HCNO, that's a conjugate pair. We have the buffer. We have the moles of each. We have the volume of the solution. And we have the Ka value. We should basically have all the pieces to just use the Henderson-Hasselbalch equation. As soon as we recognize it's a buffer, we don't need any VCA tables. We don't need any ice tables. We can just go straight to the Henderson-Hasselbalch equation. You could, in theory, if you really want to, do an ice table, but I don't know why you'd want to do an ice table and have to work through all of that. You could just plug it all into the equation and be done, right? So solving this one, kind of putting our pieces in it. Get a swap here real quick. I don't know why this thing is so laggy and fidgety today. All right. So we're told we had 0.220 moles of our HCNO, 0.410 moles of, again, sodium, like NaCNO, but really, I think of this as just CNO minus. If I ignore the sodium, I think it's much clearer to look at those two and be like, hey, that's a conjugate pair when you write it that way. And they tell us that we have 2.0 liter solution. And our Ka for the acid was 3.5 times 10 to the minus 4. Well, again, active was friendly enough to call this a buffer. I probably, like I said, wouldn't have written that in the question. I would just like, what's the pH of these two things in a solution? If I look at these two being a buffer or being a conjugate pair, so we have a buffer, that's what should lead to Henderson-Hasselbalch equation. And like any other equation, something that'll be on the front page of the test. We'll have to memorize it. And for us to use this equation then, it wants concentrations, but since it's all already in the same solution, we can just use the moles there. So we can plug the moles in this particular instance. Otherwise, things to kind of be careful of, like these concentrations in this equation, they need to be the concentrations of the things when they're mixed. But since it's all in one solution, it could also just be the moles of those things that are all there once they're mixed, either or. So in our case, we can just plug the moles in directly. We don't really have to divide, because if we divide each of them by 2, that doesn't change the ratio. So we could just plug in the moles and it should be fine. So our pieces here then, pKa would be negative log of 3.5 times 10 to the minus 4. Plus then the log of, it'll be the base, which is the CNO minus, so 0.410 moles divided by 0.220 moles. And now we can find our pH. So if I calculate that real quick. So negative log 3.5 times 10 to the minus 4 plus log of 0.41 divided by 0.22. Looks like about 3.73, I'll call that. That should be then the final pH for this buffer. Questions going through that? I think once you recognize it's a buffer, that putting the pieces into that equation aren't too bad. It's mostly just identifying that something's a buffer to begin with that we kind of have to be careful on. I will make 2 more notes about buffer solutions. So one, if you have a conjugate pair, for it to be a buffer, they do have to be weak. You can't have a strong and neutral pairing. It has to be like a weak acid, weak base kind of pairing for a conjugate pair. The other thing is you do need the concentrations to be similar. So like this ratio over here, usually we want that to be between like 0.1 to 10, so that they're in like roughly similar amounts to have a buffer solution. If you have like 1,000 times more of the acid than the base, not really going to behave like a buffer anymore. They're not kind of close enough concentrations. So the other kind of like buffer things that I'll call them almost like buffer constraints. We need kind of a 0.1 to 10 ratio of concentrations. And it doesn't really matter which way you're looking at it. You don't want one to be more than 10 times bigger than the other for it to still be a buffer. Once we get outside of that, we lose some of that pH resistance depending on what gets added. And the other thing I said is that we need a weak-weak pairing. Right, so strong acids or strong bases cannot make buffers by themselves with their conjugates, because we'd have something that's a strong acid paired with basically a neutral anion at that point. That doesn't make a buffer. We need like a weak acid, weak base kind of conjugate pair. So those are kind of the two extra, I think, limitations that buffers will have. You'll hear some other terms. I'm not big on these, but I'll at least kind of introduce them quick. Like buffer capacity is like how much you can add to a buffer and it still be a buffer. That basically means it's fitting this kind of requirement. It's like how much can you add before we break out of that kind of range of the two conjugates to each other. The other one you'll hear, I think, is like buffer range. Buffer range is limited if that's kind of the limitations on our ratios of acid to base. It basically means that our buffer is only a buffer from plus or minus 1 of the pKa. So every buffer is only a buffer in the range around the pKa of whatever the acid is. So that means if you want a buffer solution with a pH of like 7, we wouldn't be able to use the compounds that we used in this particular example, because this pKa is like 3.45, I think. So that means these two things can only be used to make a buffer between about 2.45 and 4.45. If we want a buffer that's up around 7 or 8, we're going to have to find different compounds to make that buffer out of. So things do have limitations on what pH range they'll actually be a buffer for. And it's always plus or minus 1 of the pKa is kind of what we call that buffer range. So like, for instance, like our blood being carbonic acid, I think I want to say we saw carbonic acids like Ka1 earlier today. It's around like, I want to say it's 8 something. So it's like plus or minus 1 of like that. So like usually blood's pH is around 7.4-ish. It's kind of the normal ratio. But as soon as we get away like less than 7 by too much, then we have to be very careful if our blood starts to get acidic, because now it's no longer in that buffer range. It's much easier for that pH to be affected, particularly by acids. That's why, like for athletes, things like uric acid buildup or other type of acid buildups from like caused from like strenuous exercise, like that can be a problem if you don't have ways to kind of deal with that if it lowers the blood pH too much. You'll hear things like ketoacidosis and things like that are medical terms related to really kind of blood pH and what happens to it. But I think that gets us kind of through what we're going to get through for now. For tomorrow, so for exam, I will post a practice exam here in just a second as soon as I'm done as well. I realized I didn't put that up this morning yet. It is all of chapter 15, all of chapter 16, and basically just chapter 17, like the examples that we've worked through so far. I'm not going to give anything like, it's pretty much going to be like, here's two things in a solution. What's the pH? So it'll be similar to like one of the two examples we've done where it's either just a buffer or it's like a neutralization that maybe results in a buffer, or it's like a neutralization that there's one thing left. It won't be anything beyond kind of examples we've pretty much already seen. There will be kind of one more add-on that we'll talk about titrations on Thursday, but that will not be for tomorrow's exam. So nothing on tomorrow's exam will be different than anything we've seen kind of at this point, right? So look at some of the examples. I mean, I think the homework for chapter 17, part 1, like the mixtures of the two things. I think most of those should be pretty doable already. But that way, if you have questions like that, we can go through that tomorrow at the start, like normal. First bit, just kind of questions as people have them, and we'll take the exam itself after that. Thursday, we'll get into the titration side of kind of some of these things. And then I'll have kind of one more possibility that I'm not going to throw at you just yet for these BCA tables, which is what happens if you get to your BCA table end and it turns out that your after for both reactants is 0. That turns out it can make things more complicated, because then what you have left is just a weak acid or a weak base probably, which means then you have to do an ice table after all the BCA table, which is annoying and a headache, but we will take a look at that because that's what happens at equivalence points for titrations. So we'll see that on Thursday, but nothing that complicated for tomorrow, right? questions at all for what to expect for tomorrow? If not, I will see everyone then tomorrow for our third exam. And I will be around this afternoon or tomorrow morning for questions like normal too. So.
So on Thursday, I have